Hi guys, we are going to do a new chapter today called Chemical Equilibrium. It has got a very interesting history, interesting theory, and cool numericals, very interesting ones. So I guess you guys are going to love this chapter. And before I go on to the chemistry part of it, to the chemical equilibrium per se, and which will further go on to be ionic equilibrium. A continuation of this chapter would be ionic equilibrium, where we'll be studying the equilibrium of ions with molecules and with ions. And in chemical equilibrium chapter, we'll confine ourselves to equilibrium of molecules with other molecules in a certain reaction. So before we go on to that thing, let us just understand, what does equilibrium mean? Now, if I have to study just equilibrium and I have to discuss just equilibrium without the chemistry part of it, then I'll take physical situations and study various equilibrium of a solid with a liquid, solid and gas, gas and gas. So there are various equilibrium which is possible. I'm not going to discuss all of them. I'm just going to give you a sense of what it means. So I've just taken a glass of water, and suppose I mix a lot of sugar in it. Suppose I mix a lot of sugar in it, then what is going to happen? Just let me make some sugar. So say this is the particles what I'm making is sugar, dirty sugar, so that it is visible. So I put a lot of sugar in it. You can give it a good stir and mix a lot of sugar. Eventually what you're going to see is, after whatever amount of sugar has dissolved into water, you see that this sugar has come to a constant level. It has come to a constant level, and the mass of sugar, visually you can see that the mass of sugar is not changing. The amount of sugar is not changing. So what has happened? Has the sugar stopped dissolving in? Has the sugar molecules stopped dissolving in water? No, they haven't. In fact, the sugar molecules are going into the water. Then why is the mass not going down? Because it has come to a certain level, what we say as saturation. And when one sugar molecule goes into the water, at the very same time, one, it is just a way of saying it, like millions of sugar molecules are going into the water and millions of them are coming out of the water solution from their dissolved state, from their aqueous state, to the solid state. So it was dissolved and comes back to the solid state. So this arrow is the reversible sign. It is coming back to the solid state, and initially when there was no sugar in the solution, then sugar was becoming aqueous. It was getting dissolved in the water eventually. So initially I can say it was just the solid and there was nothing dissolved. So it was rushing to get dissolved initially. So a lot get dissolved. So as soon as the concentration of sugar over here became enough, as it was increasing, the rate of dissolution was decreasing, you can imagine that. And when it became enough, then there was no longer dissolution. Now at no longer dissolution, what we are emphasizing over here is, it doesn't mean that nothing is dissolving. It simply means that when sugar is dissolving, then the dissolved sugar is coming back to the solid state. So that is called equilibrium, when the exact same amount which is dissolving goes back and becomes solid. So we can say the rate of dissolving, rate forward which was dissolving, is same as the rate backwards which was not which is becoming a solid, precipitating out. So that is one example of equilibrium. So let's see what else can be described over here. We know that water kept in a glass eventually evaporates. The water molecules are evaporating. So here there must be a lot of water molecules, and those water molecules are oozing out also. So if I keep the glass for a long period of time, say days, then the water will eventually go away. There would be no water in the glass. All would have become gas and lost to the atmosphere. Yeah, that's true. Now suppose I had put a lid on top of this glass, and now let us study what happens. So what happens is water is evaporating. Yes, water is evaporating. But then water which has evaporated becomes water vapor. Your H2 liquid becomes H2O gas. That is your water vapor. Now this water vapor is the amount of water vapor over here is increasing. Eventually the concentration becomes so high that when water goes up, when one more water molecules evaporates, another water vapor goes down into the liquid. So we say again the equilibrium has reached. So initially it was simply your liquid water, and suppose there was no water vapor on top, you always have some humidity of the air, but suppose the air was dry on top, then what was happening? Water liquid was in a rush to become water gas, which is water vapor. And as the density over here increased, this rate decreased. It seemingly decreased because what was happening is, as soon as you have some H2O on top, some H2O on top as gas, as vapor, it is some of them is bound to go back and become liquid. It is not necessarily that it achieves equilibrium and then it starts going back. No. The thing is, initially lot is becoming vapor, and the ones who have become vapor are less in concentration, less than the required concentration. So only few of them are going back and becoming liquid, not as much as were becoming vapor. Vapor, it was more which was becoming vapor and less is becoming liquid. Eventually, when your water vapor over here increases in quantity, increases in concentration, then the rate at which it is going to become liquid is also going to increase, and the backward rate eventually will become the forward rate. The rate of condensing will become the rate of evaporation, and it would seem as if nothing is happening. The mass of water will remain as the same. It is not going to lower any further, and the amount of gas is going to remain the same. So it seems like nothing is happening, but a lot is happening. Lot of water is evaporating and lot of water vapor is condensing. So this is again an example of equilibrium. Water with its gas, liquid with its gas. So there are several cases of equilibrium. You can have a container with, say, solid, say I2 solid. I2 solid directly changes to gas since it is sublime, and then this can go back. If it is a closed container, then that gas eventually, if it is enough, then any more sublimation is going to make the gas freeze back and become solid. So this activity, even though you won't see any change in the mass, you may see the change in the shape and all, which is going to depict that yes, equilibrium was there. But I hope you have understood a bit of what is equilibrium. And so you can have equilibrium of, I'll give you another example. I'll give you an example of a gas which is not water and getting dissolved in water. Like here itself, if I say there is oxygen in the air, oxygen is not water, oxygen is in the air. Is oxygen dissolved in water? Yes, it is. It is dissolved in water due to a certain pressure of the oxygen in air, say around zero point 0.2 atmospheric pressure. That's the partial pressure of oxygen in air. Some of oxygen has dissolved into this water. Now, is the oxygen inside water going back into air? Is this oxygen going back to air? Yes, it is. There is a equilibrium reached. So the dissolution is not increasing, but it is not like further oxygen is not going in. Oxygen is going in, is dissolving in water, and the dissolved oxygen is going out, and there is an equilibrium between them. This can be very well noticed if you watch carbon dioxide in pressurized containers. You may increase the amount of gas dissolved, say CO2. As such, it will dissolve more than O2. All of this you are going to study in a chapter, in a separate chapter, and that chapter is called sorry, and the law under which we are going to study is called Henry's law. That is going to come next year. So we are going to study where gases are getting dissolved in water, in a liquid, and the amount of dissolution depends on how much is the pressure. So to dissolve carbon dioxide, we'll rather have a closed container, and we are going to pressurize it so that the dissolution is increased. So that is, if we had a certain equilibrium, which way we are wanting to shift the equilibrium. So that is also a study which is going to be done in this chapter under La Chatelier's principle, where he understood that equilibrium can be disturbed by disturbing various factors, and then he wanted to utilize that to have in fact he utilized it for good effects. So I guess you got an idea of what is equilibrium, and let us go on to chemical equilibrium, which is the actual agenda for today. So way back in 1803, Berthollet had developed the concept of chemical equilibrium when he saw that when he figured out that reactions were reversible also. Some of the chemical reactions were reversible also. The say A and B is giving C and D, then that C and D can give back A and B also. So that opened up. So that opened up the study towards chemical equilibrium. And then we had a very smart chap named Le Chatelier who who became an authority on study on equilibrium, did a lot of study on this. Basically, once you get to know a concept like chemical equilibrium, how can you utilize it for making useful stuff for benefiting the mankind? Like an example we discussed, when carbon dioxide has to be dissolved in water, they are dissolved in pressurized containers. Your soft drinks are having a lid which can hold a certain pressure, because increasing the pressure increase the dissolution of CO2 in water. Now this is not a big help to the mankind, but uh, uh, Coca-Cola is or was one of the biggest companies ever. So and what is this? What is this? How was that achieved? By understanding how you can shift the equilibrium achieved of a certain reaction on towards a certain side, say towards the right side or towards the left side. You can call anything as a product and anything as a reactant, but when you generally write the chemical reaction, the left hand side is where we write the reactants, and right hand side is what we generally call is the product. And here you are seeing that both the sides are reacting and giving the other side. So those terms becomes a little dicey. So we have Chatelier's principle, which we are going to do in detail, which is in a way talking about how a equilibrium gets disturbed when certain factors are changed, like pressure, concentration, and other things. So we are going to discuss that. And while discussing chemical equilibrium, worth mentioning is this equation: nitrogen plus hydrogen gives ammonia, and ammonia gives back nitrogen plus hydrogen, because ammonia, as you know, is very useful, a very useful compound. It is used in fertilizers all over, and all over the world. And getting ammonia through a reaction is a boon to the mankind. And initially, and when we are going to discuss chemical equilibrium, then a special mention of this reaction is a must, I would say. Nitrogen, hydrogen combines and gives ammonia, and ammonia breaks back and gives nitrogen and hydrogen. So why this is having a special mention? First of all, ammonia is a very useful chemical, which is, as we all know, currently all over the world it is utilized in making fertilizers. So it has many other use. So and it has benefited, the manufacture of ammonia has benefited mankind like nothing else. So in fact, last Chatelier was trying to shift this equilibrium towards the production of ammonia. He was trying to utilize nitrogen we have in air. H2 we can get from a lot of sources. So both the ingredients are easily available, but making ammonia is not so easy, because the equilibrium is heavily towards the left side and not towards the right side. So how to do that? So Chatelier had all his principles. He wanted to apply them, and he was applying them and trying to make this. He could not. He met with an accident also, and he says it was a regret of his life. And the person who could do it, by the way, is again very famous, and has won Nobel Prize for it. So I guess you would have guessed it. So Fritz Haber, the German guy who had made Harbor process, who had devised this Harbor process, which was a successful way of changing or creating ammonia from air, from nitrogen from air, basically. So you take air, you take hydrogen. Hydrogen is coming from methane. So from methane and water, you're getting hydrogen and carbon monoxide. All these reactions either you would have done in class 10, or you are going to do. This Harbor process was for ICSE board guys in class 10. So now you have the ingredients. Now you can see how much of it takes to get your liquid ammonia over here. So what are the key things, key factors in here is high temperature catalysts, and um, high pressure. I guess it would be mentioned somewhere. Yeah, there's a 300 bar pressure and 450 degrees Celsius, which is in the reactor. So if you increase the pressure a lot, if the temperature is a lot, then this is what is going to come, and that too not a lot. So you are recycling it. So this was a process which won him the Nobel Prize, and it opened a lot of possibilities. Yeah, unfortunately, it led to Germany raging havoc in your World War One. Genius that this guy was, He gave Germany an option of creating explosives. Nitrates are required for explosives. I hope you know that. And the supply of nitrate had stopped when they had gone for war. Britain had stopped the supply of nitrate to them. The path was stopped. So and nitrate mainly it was coming through chili saltpeter. Chili saltpeter is sodium nitrate. It is naturally occurring in chili. So that had stopped, but ammonia, production of ammonia gave them away. Once you have ammonia, it is very easy to oxidize this and produce nitrates, which can be made into explosives. So gave a big advantage to Germany. And uh, and then this guy Haber, uh, genius that he was and patriot also, he had devised, he can be called the father of chemical warfare, where he had devised ways of poisonous gas in the warfare, like chlorine. And you can see even the horse has to wear a mask. So in April 1915, the first chlorine gas attack was carried out in Belgium, and supposedly under his supervision, under Haber's supervision. So you can see how geniuses can be on the verge of becoming villains. And a very controversial Nobel Prize of 1919 went to him just after the war, when he has been called the father of uh, chemical warfare, where millions and millions died, mostly the civilians. So, anyways, coming back to, so chemical equilibrium has a very interesting history. And another very interesting information is that he was Jew, and after the First World War, around 1930s, he had to flee Germany, and the ways what he had devised for destroying the enemy, the same ways were used on the Jew. The Holocaust, you must be knowing, and his own relatives died uh, in those ways, whose father was Haber himself.